In my last video, we went through some problems of the chapter round on MathCounts Trainer. Now, if you want to learn and do some MathCounts Trainer, I will put the link in the description for MathCounts Trainer, as well as the Art of Problem Solving. Really good website, teaches you a lot. It's a lot of advanced math. Today I'm coming to you with the school round video. This is different from the chapter round. This will just help you get ready for school competitions. Okay, these are like warm-up problems. These are the difficulty of these problems are easy to medium easy, so let's do this first one together. I will show you how to do it two ways, so let's begin. When Will was 5, his allowance was 25 cents. When he was 6, his allowance was 50 cents. If Will's allowance continues to double each year, what is his allowance at age 11? Now, there are some ways you can do this, so please pause the video, and then I will show you how to do this question. Okay, so you just pause the video, and we're back, and here's the explanation. So, what we can do here is say, if when he was 5, his allowance would be 25 cents. So let's keep track of his allowance in a table format. So when he was 5, his allowance was 25 cents and doubling as he kept going. So when he was 6, he had 50 cents. When he was 7, he had $1. When he was 8, he had $2. When he was 9, he had $4, 10, 8, and finally, when he was 11, he had $16. Now, even though they do ask for that, we're going to prove it in a different way. Let's suppose they ask how much allowance he has when he's 100 years old. Then we can't keep counting like this because that would take way too long. So let's figure out a better way to do this. Let's look at a geometric sequence formula. A times r power n minus 1 is equal to a to the nth, a of n. A being the first term, r being the ratio. So now we see in A that A is 0.25 since he starts off with 25 cents. What is the ratio? Well, he gets double allowance each as he gets 1 year older, so the ratio is 2 power n minus 1. N being, now you have to be careful here. N isn't how old he is. So in this case, if we were trying to find 11, n wouldn't be 11. So I'll show you. It has to be how many years since he's gotten his first allowance of 25 cents. So when he first got 25 cents when he was 5 years old. Now we're trying to ask how many years it's been now that he's 11. So if we subtract 4 from 5, we see that it's 1. So that gives us to when he was 1 year old. So now we have to subtract 4 from here. So that means it's 7 years. So it's the difference since he's gotten his first allowance. So n, in this case, n would be 7. So 2 power 6 times 0.25. 2 power 6, as I put up here, is 64. 64 times 0.25 is 16. So now let's do the question that I asked in the beginning. What would his allowance be if he was 100 years old? So it would be, let's go over to our calculator, 2 to the power of 99 times 0.25. So when Will is 100, Will would be rich. Okay. So, next problem. The answer is 16. Okay, the sum of two numbers is 13. while their product is 36. What is the sum of their reciprocals? Express your answer as a common fraction. As usual, pause the video. Okay, you paused the video, you solved the problem, or you at least attempted to solve the problem. You had a strategy, and now you're ready to see the explanation. If you already solved it, please don't skip over the explanation because you could find out another way to do the problem. Now, in this case, when you were thinking about your strategy, you probably noticed that you can do it algebraically, but eventually it's going to come to the same thing as guessing and checking, and I'll show you why soon. So first, let's write out our cases. A plus B is 13, and AB is 36. Now, why did I just say that the algebraic way of guessing, of proving that A is equal to 13 minus B, it always comes back to guessing and checking. I'm going to show you why that's true right now. So let's manipulate this equation. A plus B equals 13 is the same as saying that A is 13 minus B. Now let's plug this into this equation. So we have 13 minus B times B is 36. Now, multiplying this out, we have 13b minus b squared equals 36. And since we want to make this into a quadratic equation so we can factor out, we have to bring the 36 over to this side. So our final equation is negative b squared plus 13b minus 36 equals 0. Now, it comes to, you can either do your quadratic formula, or you could find the easier method, which is trying to find factors that go into this by doing two numbers that multiply to negative 36 and two numbers that add to 13. Now, as you can see, what I've written right here, these cases to factor out this quadratic are the exact same cases of our problem. Except we find that this is negative 36, but it doesn't really matter. It's basically the same cases. So instead of the only point in factoring it into a quadratic would be to use the equation. But let's not do that, since it really, there's no point in doing that. So, rewriting. Okay. So, first thing we want to do in this case is look at our multiplication case right here. And we want to analyze the factors of 36. So, I've written it down right here. We've had 1, 2, 3, 4, 36 is a perfect square. So, it has an odd number of factors. 9, 12, 18, and 36. Now, all we have to do is simply pick out the two factors that add to 13, which is 4 and 9. So now the question asks, what is the sum of the reciprocals of 4 and 9? So 1/4 plus 1/9. Multiply to make a common denominator of 36. And our numerator is 9 plus 4. So the answer, 13 over 36. Okay, so that last part of that problem got cut off, but our answer was correct. Okay, next question. Miss Smith teaches for 5.5 hours each day. If she teaches for 6 days, how many total hours does she teach for? This should take not that long, so pause the video. And Miss Smith teaches for 5.5 hours each day. She teaches for 6 days. How many hours will she teach? So, 5.5 is the same as saying 5 times 2 plus 1 over 2, which is 11 over 2. And why can we do that to fractions? Why can't we just multiply and add the numerator and then say that that's how many there are? Well, we can look at how many halves are in 5 first. So this is like some big proofs here. This is like some basic proofs that really go into something that we use so much. How many halves go into 5? Well, we know that there are 2 halves that go into 1. So if there are 2 halves, this is the amount of halves that go into 1. The amount that goes into 5 is 10. So what if we have 1/3? How many thirds go into the number 1? There are 3 thirds that go into 1. So how many are there that go into 5? There's 15. That's why we multiply. So that's only part of it. That's why we multiply 5 and 2 to say that it's 10. But why do we add 1? Well, when we add 1, it's more like saying we add 1/2. The 1, so basically why we're doing this is when we multiply, so let's get a bit tidy here so I can show you guys. So we already saw why we multiply. So in this case we have 10 over 2 so far, but now we usually multiply and then add 1. But technically we're actually adding back the fraction, and that is what gives us 11 halves. But a shortcut that we can do is we can multiply this constant number 5 here by 2, since we know that there are 2 halves inside 1. So using that ratio, we know that there are 5 times 2 halves in 5, and then we're going to add back this fraction of 1/2. So that's 11 halves. And then if she worked for 6 days, that's going to be equal to 66 over 2, or 33 hours. Okay, those were some warm-up questions. Thank you for spending time and taking the time to watch this. If you want to do the problem on the screen as a last problem of the day, good job. That was a great warm-up, but now you can go and watch the chapter run video, which is going to be a bit harder questions. And then if you like these videos, comment down below and tell me if I should do there are different rounds on MathCounts Trainer, so like I can do state and national. I haven't done those, and I haven't even unlocked national. So tell me if you want me to do those. Thank you so much, and see you later.